Okay, very good afternoon to everyone. Welcome to lecture 8. We'll continue on convexity and first order properties, and we already started discussing second order properties. So this is the outline. After understanding convexity of certain machine learning loss functions, we plunged into first order properties through the notion of directional vector and directional derivative. Uh, the connection here is very important. We really started talking about the directional derivative from the point of view of increasing values of the gradient for convexity, or you could also think in terms of the second order properties as increasing curvature along any direction. But in both cases we have a notion of any direction. Okay, and therefore there's a notion of a direction vector. That's very critical. So directional vector, as I said, both directional derivative and curvature are hinged upon directional vector. Okay, in terms of the convexity, when we talk of cup shaped, right, that cup shaped property could also be realized using a lower bound. The lower bound or the supporting hyperplane at any point, its existence is guaranteed by virtue of convexity. Now the supporting hyperplane is to a set we define to be the epigraph. So this is the epigraph of the function. What we have here is supporting hyperplane to the. A related question we had was what if the function is not differentiable, right? And that's where we started talking about the fact that by supporting hyperplane theorem, there is a supporting hyperplane to the epigraph at every point, even if f is not convex, because if f is sorry, even if f is not differentiable. I'm sorry, I should just change it. Even if a convex x is not differentiable. So convex x or f would imply that the epigraph is convex. It may not be differentiable yet. By supporting hyperplane theorem, which I'm not going to prove, there is a supporting hyperplane at every point. Okay, and so that means there is an equivalent of the gradient. There is an analog, generalization, I would say, generalization of the gradient called the subgradient. Okay, so that's what we kind of have here: subgradients, subgradient calculus, and convexity. But let's continue on this to complete our homework problem. Okay, so we also defined this Hessian, and then we showed that f is convex if and only if the Hessian is positive semi-definite at every point. It's like saying that the quadratic expansion, which corresponds to the curvature along any direction v or any slice v, it must be positive. That curve is the function is curved upwards in along any direction. Now, for the specific example of log sum x, I had requested you to attempt this homework problem. Instead of, you can certainly derive the Hessian, but I said, well, how does the quadratic expansion look like? The curvature along any direction. Did anyone attempt this? Did anyone try deriving this?
Yeah, I got the Hessian.
Okay, great. You derive the Hessian, you're saying, is it?
Yes.
Okay, and what does it look like?
I got the same result that you showed in the next slide in that table of your notes. I got the same result.
You
Yeah.
got this result.
Yes.
Okay, yeah. This 1 upon 1 transpose z square in denominator. Then there's 1 transpose z, which is basically sum of all elements in z times diagonals of z minus zz transpose, where z is nothing but e, the vector of e raised to the different components of x. Okay, this is log sum x. I mean, this xk itself could be w transpose something else, right? So we have simplified it here. I mean, xk itself could be a linear function. So we have simplified to that extent. Okay. Fine. But what about the quadratic expansion? Did anyone try that? Did anyone try the quadratic expansion? Okay, let me just present the quadratic expansion. Okay, so as I asked as homework, what we will try and do is express this. Right? And how will we express this? We will basically express this as V transpose Hessian V. Okay. Because to show that this is positive semi-definite, you have the Hessian. But to show that it's positive semi-definite, it's going to be a little difficult. Whereas this, we will show that this is greater than equal to 0. For all V. Okay. Okay, so let's try doing that. On the next slide, I'll do that, doing that. I mean, what you'll do is basically take this Hessian expression, pre-multiply by a V. Okay, now that when you pre-multiply by V, your V can actually go inside. Some of these are scalars. So note that some of the components here are scalar, like 1 transpose Z is a scalar. Okay, so let's just mark all the ones which are scalars. This is a scalar. In fact, this component, these both are scalars. And what else is a scalar? So you can basically push the V into the scalars, correct? And you'll push basically V as far as this component here. So your V will basically reflect in diag here, diag Z. You worked it out, that's great. ZZ transpose. So ZZ transpose is a matrix. Diagonal Z is a matrix. Everything else is a scalar. Okay, so just making my observation. The V can be pushed into multiplication with yellow highlighted matrices are scalars. That is a good bit of a relief to me. So what would the expression look like? Any suggestions? Let's in case anyone has written, please let me know. Otherwise, we'll have to use the next page to write this down. Let me see if I can write it here. It'll be better. Just move this here. Okay, let me try and write it here itself. Okay, so let's write down this expression. So you'll have denominator is 1 transpose z square. Okay, there's 1 transpose z inside will also stay back, but I'm going to write it slightly differently. I'm going to write it as summation zi. Okay, I equals 1 to n, and there's going to be a, so this is a smaller component. I'll just use some color coding here. So this part I'll highlight it in orange, and then we'll have the next component. Let me use a slightly different color for these two. When I expand diagonal z, okay, so I'll have diagonal z I mean v transpose v. Okay, so both need to be factored in, and that should amount to summation over I equals 1 to n of v coming from the v on the left, and then vi coming from the v on the left, and vi coming from the v on the right. That will lead to vi square zi, because it's a diagonal matrix. Like, I mean, basically v transpose diagonal z, v is just going to give you the squared terms in the diagonal. You can verify that. Okay, so that part is this part in pink, and then the next component minus the zz transpose. What will that correspond to? So zz transpose is a rank 1 matrix. Now basically have, okay, so if you want you can write this v transpose z. Okay, let me write it here itself. V transpose z into z transpose v. V transpose z is a scalar, z transpose v is a scalar. So what you will get is a scalar square basically. So the same as v transpose z scalar square. Okay, that's nothing but summation over I 1 to n of vi zi square. Suddenly things start simplifying so much when you have the quadratic expression. Right? So this entire thing is this part. But of course, z transpose into va pre multiplied by v transpose post multiplied by v. Okay, so much for this. And then what is this basically? So if you take let's say I just set vi into root of square root zi. Okay, if I set to x vi into square root zi, and set y, sorry, this should have been xi. This is xi. Similarly, yi is the square root zi. Is some substitution basically. Now what does that yield? Okay, again, let me use some different colors for these. So let's say I shade this in gray and I shade this in blue. Okay, now I'm going to just substitute. Let's see what happens. Sorry.
From here only we can directly say by Cauchy-Schwarz array.
You can do Cauchy-Schwarz directly, or you can just do this additional step. Yeah, but this basically is now going to exactly what we did earlier, right? First principles, but now you see the same thing manifesting in the Hessian. So x transpose x, this will just become x transpose x. Right, this part in pink, and what else will happen? This part, actually I should write down this. This is y transpose y, right? And this part minus is x transpose y squared. Okay, so we have everything in place. Um, okay, so yes, as somebody pointed out, you may not need to go so far if you could easily see through. But this is basically greater than equal to 0 by Cauchy-Schwarz inequality. Okay. Yeah, let me just move this. Yeah. Okay, so we are back to what we had. So I hope you got the homework problem. Anyone else wants to comment? Yeah, thanks for identifying that. No, this is very obvious. So this is very reassuring for us as well. I mean, we found two different ways of proving the same thing. Log sum x is convex. Log sum x is very important for us for machine learning, and we see that both the proof methodologies are very similar at some point of time. However, they made use of two different results. Okay, so that's okay. Is it just convex or something more? Is it strictly convex? Can I say strictly convex? Because equality will hold only if y and x are the same. Yes, can someone help? Can I say strictly convex? Okay, so I'm going to leave a question mark unless one of you stands by or defends strict convexity. I'm going to leave it at this. Okay, so we solved the homework problem. And then we recap that we said that a function, if it's differentiable, then we say that there's a supporting hyperplane, but that supporting hyperplane or the supporting linear tangent that underestimates the function will be unique when the function is differentiable. Otherwise, at all other points like this, we saw this example last time, it may not be unique. Okay, now of course I've shown the function on the left hand side here. Is this really a subgradient? I mean, so we generalized the notion of gradient to subgradient, but the example on the left hand side, is it really an example of that generalization of subgradient? Yes, anyone? So this L that I have shown here, yes. Of course, L will not be a subgradient, but is L based on a subgradient? All?
In the case of L, won't
Yes, sir.
both the perpendiculars be the same?
Won't the perpendicular to?
The perpendicular that we're drawing,
Hmm.
won't they be the same? So it's the single line that's there.
Yeah, but do you? I mean, is F even convex? Is it possible that if I extrapolate the L, this line here, it will intersect the F? L should
Yes,
be a lower bound, right, to the entire function,
yes, it will cut F.
right? So F is not convex, right? Hello, am I audible?
Yes,
Yes,
sir.
sir.
F is not convex, sir.
Yeah, F is not convex, and hence L does not is not a subgradient. I mean, it's a hyperplane that is locally supporting, right? But it's not a subgradient to the function globally. And we can think of it as local subgradient, right? But there's no, I mean, we will desist from talking about that right now, given that I've shown the entire function. So given that I've shown the entire function, it's really not a subgradient or a gradient for that matter. So just because it's differentiable doesn't mean that you've got a supporting hyperplane. And just because the function is not differentiable doesn't mean that it doesn't have a supporting hyperplane, right? So let's be, I think that's important to as a function being differentiable not imply that it has a supporting hyperplane at all points. Okay, so I hope this point has come out clearly. Okay, so let us proceed if there are no questions.
Sir, that means every f will have a gradient, but not necessarily a subgradient.
Exactly. Every f will have, I mean, every differentiable f might have a gradient, but that
And every
gradient is not
convex
a.
will have, yeah, every convex
It's
function will have subgradient.
that gradient may not yield a supporting hyperplane. On the other hand, the notion of subgradient is based on supporting hyperplane, and we are saying every convex function, even if it's not differentiable, will have a subgradient at every point. Is that okay?
Yes, sir.
Okay, so that's what we are coming to the next. On the other hand, every convex function will have at least a subgradient at every point, since subgradients generalize the supporting hyperplane, that gradient provided for the convex functions. Okay, gradient provided only for convex functions is supporting hyperplane, but for convex functions we are able to generalize. Okay, so this every convex function, even non-differentiable. Okay, so this hopefully I've tried to reinforce the same point in multiple words now. And what we moved to in the last lecture was this generalization of this gradient. So we are saying this is no longer a binding cause for us. We're just going to replace this with an h. Okay, so we'll just call it an h. Okay, so let's have that. So that's exactly what I showed here. This is not even a differentiable function. Okay, so this has, I mean, this turns out to be max. Okay, so we all have familiar with max and we know max is convex, but let's nevertheless, identify that, this is a function f1. On the other hand, this part is a function f2. Right. On the other hand, at this point, which turned out to be the max, and in fact, the function itself is the max. This point is where the two maxes coincide. Everywhere else, there seems to be a unique max. Okay, so this f is basically max of f1 comma f2. And what we are claiming here is that this I mean, this has regions of unique subgradients. So this is a region of unique subgradient. Likewise, there's another region it has of unique subgradient, that is this one. But the part here in blue is where the two subgradients coincide. The functions coincide. This point has the two function values coinciding, hence subgradient is not unique. Okay,
Sir, is L1 and L2 seen as an extension of the F1 and F2 functions?
no, they are L1 and L2 are both supporting hyperplanes.
Okay.
Right. In fact, the supporting hyperplane, sorry, subgradients form a set. It's called the subdifferential, which is the convex combination, convex hull rather, of the gradients to F1 and F2 at that point. So in fact, that's what we are seeing here. We saw that there is a shaded region, right? And that shaded region basically is a convex hull. It's basically all possible convex combinations. This region, convex hull. Okay, so I'm just going to read and say that this is H. So it has a name. It's a space of all the subdifferentials. Is denoted by partial F. Okay, so there are lots of H, lots of subgradients which belong to this partial F. I mean, this itself is a set. There are lots of H in this. Okay, but on the other hand, if a convex function is differentiable at a point X, then what do you know? Then yes, unique, right? And what does it correspond to?
Gradient at that point.
The gradient at that point. That's what we found. Region of unique subgradient are the green and the pink regions. Okay, so yeah, and the proof for this, I had pointed you to my convex optimization notes. I'm not going to go over it. Right. So and this is a claim that for a convex set there exists a supporting hyperplane at each point, and the supporting hyperplane is unique when the boundary is continuous. So when we say that when the function is differentiable, then we are basically saying that the boundary is continuous. That's the same. Function being differentiable and boundary being continuous. This boundary. Okay. So it's all very interesting when you especially do a mapping to the geometry. So otherwise we'll proceed. Okay, so the proof I have given in my notes, I'm not going over it. How differentiable convex function has unique subgradient. It's really advanced and optional. This epsilon delta, which we have used always, right, for showing or deriving limits, etc. That's what we are doing here. Okay, so let's move on, unless you have some questions. Okay, so now just a small detour which is very related to convexity and continuity. So we said that the boundary, in some sense we said, right, that boundary is continuous. Boundary continuous and function being convex. What's the connection? What's the connection between domain being open and F is convex? Well, it turns out if the domain is open and f is convex and f is continuous, okay, and how wild can differentiable convex functions be? So it looks like convex functions in general are very well behaved. Okay, that's an interesting side thought. A convex function is differentiable almost everywhere. I mean, with the set of points where f is not differentiable is very small, measure zero. Like you do a probability is a instance of measure, right? So it's like giving you cardinality in some sense functions. So it's very small. Uh, However, we cannot ignore non-differentiability because the global minima could be a point of non-differentiability, right? And that specifically when we are dealing with, say, constraint optimization. When you're dealing with very activation functions which are not continuous. Neural networks, when the activation functions are not continuous, you are never anyways not talking about global convexity everywhere. You're still talking about local convexity. But even with local convexity, you may have to deal with the non-differentiability. In lots of conventional optimization, I would say even recent optimization, conventional machine learning and recent machine learning, and we are dealing with constrained optimization. I mean, activation functions not being continuous, ReLU is one example. Many others are there. ReLU is very effective. Okay, so hence for these reasons we cannot simply ignore the non-differentiability. Okay. So now coming back, so therefore dealing with non-differentiability is important. We go back going back to subgradients. Subdifferential is a set of all subgradients, and it happens to be closed and convex. So closed will basically mean that it will contain its boundary. Okay, so very simple. We are going to look at very intuitive understanding. So closed will mean that contains boundary. All of you know, right? 0,9 is open, whereas this square bracket 0,9 is closed. So it's a closed set, and it's a convex set. So as I said, uh, you can think of the subdifferential as a hull of multiple gradients, convex hull. So it's always a convex set. So subdifferential is a convex set and it's closed. Yeah. And very related to what I was saying earlier, every convex function has a subdifferential. Basically, this set is guaranteed to be non-empty. It will have at least one element when f is convex. Okay, now it is not that if f is not convex, then this set will be empty. No, I mean, we saw an example here. This is an example of a non-convex function. It didn't have a subgradient here, but it has a subgradient in other places. Okay, so let me in fact, so let's take that example. Let me just copy this example. Okay, so let's go back to this example. So this function doesn't necessarily have empty subdifferential everywhere. Okay, so but it certainly has an empty subdifferential here. and in several other points places, right? However, the subdifferential is not empty in, say, here, this region, for, I mean, in fact, for a large part, almost until this point, this function does not have an empty subdifferential. So you can think of this region as a convex region, right? So in this region um, of convexity of the function, okay, it's not that a function, if it's not convex, it will always have an empty subdifferential, as you can see in this example. Okay. Let's take some examples. I already started this off in one sense. I took that motivating example for a subgradient, but let's take a more specific example. So pointwise maximum. So if fx is max of multiple functions, then the sub differential is actually the convex hulls, is a convex hull of the individual functions subdifferentials. Now, if the fi's are themselves convex, then this basically boils down to what? Yes, anyone wants to answer? So if fi's are not convex, if fi's are convex, which they will be, let's say that's already assumed, right? And differentiable, then what happens here? Then what will be the subdifferential of f at the point x? So convex hull of
Gradients.
gradients. Now, one small point here, it's only of those gradients here which give you the max value. So good point. It's gradients, but qualified. Okay. I should just tilting it too much. It's a union over indices I, where fix equals fx. The places where it takes the max of the gradient of fix. Only those, not all are contributing. Okay, so just pay some attention to the index set here. Other than that, you're right. I hope the intuition is clear, right? These are the active functions. Okay, the places where the functions which take that max value are said to be active. So I'll just make this point here. If fx equals fix equals fjx, fi and fj are said to be active at x. Okay, so this should make intuitive sense to everyone here. Now, moment I say convex hull, then we are also making one more assumption here. If you take two subgradients of a two distinct subgradients at a point x, then is there convex combination subgradient? Yes. The related question is the convex combination of two subgradients at a given point x also a subgradient? Anyone? What do you think? Always. I mean, this is always, not just in the case of convex hull. So what do you think?
Yes.
Yes, it is. So that's true, and that can be proved from first principles. Okay, so think about it. I'm not. I may leave it as a homework, but you should prove it. Answer yes. Provable from definition. Okay, what is the definition we are talking about? The definition is that H is a subgradient. Like let's say two subgradients. Let's give them name, right? So let's give them name H1, H2. Okay. So we know from the definition that we are talking about H as a subgradient if f of x is lower bounded by f of x dash plus h1. So this is or rather I should put it the other way. I'll put f of x dash greater than or equal to f of x plus hx. So or h1x for each of these, h1x transpose x dash minus x. Okay. This holds for h1, this holds for h2. Okay, now it's easy to show that if you take a convex combination of the two, then you're doing well, right? Let me. Okay, so imagine I did a convex combination of the two. I did the same thing. Now I just replace h1 with h2, and then you're done. So yes, that should hold trivially. So you'll have to just do theta 1 times the first one, theta 2 times the second one, and then still the 1 minus theta 1. Let me use theta times this and 1 minus theta times the second, and then you're still in shape. Okay, so that holds. So overall, the picture we are talking about is as follows. If you're dealing with, say, active functions and the convex hull, let me just. Okay, so this basically correspond to like this. Okay, so you have there's a notion of tangent cones here. Just enlarge it. Okay, this is what you're saying. So you have these two active functions at a point here. You're taking the convex combination, and that's what gives you this shaded region. Right, the boundaries will correspond to this one. The pink one, for example, is given from the gradient of f2, and the blue one here is coming from the gradient of f1. Okay, so this is the overall picture. Any questions? Otherwise, we'll move on. We are done. Now, in general, a pointwise maximum over a potentially infinite set S, right, of indices, that is also going to give you. You always have a subgradient or sub differential as a set, but you need some regularity conditions, which I'm not going to talk about. I mean, some very simple conditions that you need on S, and it turns out that it's the same. The only difference is that here you had just a convex hull. Here you're saying the closure of the convex hull. So remember, the subdifferential we said was a closed convex set. So closed is coming out here. So if it is not closed, you have to close it. That's all we are saying. Because if it's an infinite set, then it might happen that it's not closed, right? By by design. But then the sub differential must be closed, so you'll have to close the convex hull. Any questions? And we've seen examples of this in the past. For example, if you take well, if you take the max of singular values, then it's okay, right? But you could have, let's say, very large dimensional space of vectors on which you're seeking the max. So we for example, we saw the sum of r largest components. That's fine, right? But there are cases like this vector case, right? Where, if I have, I mean, we saw the example of matrix norm. There, you really had an infinite number. So you vector induced matrix norm. Okay, so what's the example of vector induced matrix norm? We saw some examples, right? The spectral norm, the nuclear norm. So we had MA, right? MNA rather, was supremum over V not equal to 0 of n of AV divided by n of V. Okay, this is an example. The max over infinite indices here. So in this case, you'll have to explicitly do a closure. Of course, in this case, I mean, if you want to compute the subgradient, many of these norms might be differentiable. But for example, L1 norm is not differentiable everywhere. Okay, so if n happens to be L1 norm, since it is not differentiable everywhere, yeah, this result can be handy. Okay. Okay, so let's take some example. Now we are going to specific examples. So let's say one norm itself, right? So if x is in Rn, then one norm is what? Is there another way of writing one norm? We have done this before. For example, the sum of R largest components, we wrote it differently. Can I write the one norm differently? And then therefore compute its subgradient? Anyone? Yeah, please help me. Can I write this one norm as a max over potentially, I mean, not infinite, potentially infinite, but also very large number of functions? Is anyone?
Max over an inner product, or because you have to
Max.
sum the absolute values. So max over some V transpose X, where the elements of V can be 1 or -1.
Excellent. V transpose X, where V is a -1 plus 1 raised to n. Okay. Good. Does everyone get that? So you have to know that this one norm is nothing but max over all possible signed combinations, right? A max of x1 plus x2 blah 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 blah, x1 minus x2, we don't know depending on the sign, right? I mean, so or it could be minus x1 plus x2 blah blah blah, right? If just in the case of just two values, right? Or it could be minus x1 minus x2. Now this all of max over all of these is exactly the absolute sum of absolute values. Absolute value of x1 plus absolute value of x2 blah blah blah. Okay, so that's the reason we have a we have written this very compactly. So basically it's max over this. I've used S instead of B. It's a pointwise maximum of 2 raised to n functions. Okay, so I mean, if you want to expand this, expand it further, yeah, but it's just very time consuming. But let me just try and quickly depict it, right? How will it look like when you expand it? Basically, you have 2 raised to n functions here, sitting here. Each of them will look like -1, blah 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 into. So let's say I have a vector -5, -6, -7, -10. So 2 raised to n such configurations, and at different points the max could be different, right? So at this point the max corresponded to certain configuration of S. At this point there's a different configuration that gave you the max values. So each of these configurations corresponds to one of these different points, right? And these 2 raised to 1 functions is basically the same as saying or configurations. The function basically of S. Is this clear? So given this, I've just taken this example. So if there's question, let me know. I'm just giving an example here, right? If you have something like x equals -105, s equals -1, s -1, -1, 1. Okay, so now in this case, what happens is both of these configurations give you 6. So there could be multiple functions that give you the maximum value at any point. Okay, so this implies at a point x, there could be multiple function indices or s indices which yield that maximum. Get to everyone? Let me know if you have questions. I'm just trying to give a motivating example here. Okay, so given this, let me actually move this to the next slide, right? This is where it's. So I'm basically saying this S star is a set of such indices. All these indices where the S, all those S's in S star give you that maximum value. So this is called S star. You can actually index it by X, is S star X. At a given point X, all of these give you the set of S such that for each instance S star, the value of X transpose S is the same max value. So ideally it should be written as a function of X. But just too cumbersome, we have dropped it. Is this, let me know if you have a question here. So if this is clear, we'll proceed. The star A is all those which give you that peak, the max value. You can write your own functions. So what we did earlier, therefore, is we said, well, for all these guys, we'll need to come up with a convex hull. Right? That's by calculus of subdifferentials. This is exactly called calculus of subdifferentials. By invoking calculus of subgradients, subdifferentials depends on, both are the same set of subgradients and subdifferentials. So what did it look like? Might recall that this is well, in the case of just the two lines here corresponding to two S's. At this point, these two, both of them are maximum, and now we are talking about the convex hull. So our expression is the convex hull, and those two indices, basically S star here corresponds to these two curves. So you could have had a third curve which may not peak here, right? Or a third index. So at this point, this is the S star X. Okay, so this are we talked about. That's exactly these two. This one and this one. Okay. So now let's look at some more subgradient calculus. We saw addition is always going to give you addition of two subgradients is going to give you a subgradient if the addition is with respect to positive terms. You can't have the difference of two subgradients to be a subgradient. So it's positive or convex combination is what we saw earlier. So this is generalization. Okay, so the second one is generalization for earlier statement that convex combinations of subgradients are convex. We say any positive linear combination of subgradients is also a subgradient at a given point. Okay, so we can't just change the point. X has been assumed implicitly here. In fact, all the statements are about a given point. Okay, and it's easy to see scaling is also basically going to give you a subgradient. It's a simple case where you have only one function instead of two functions. Think of scaling as a special case of the second point I have talked about. So again, this is very simple. Unless you're going to ask, I'm just going to leave it. Straightforward from definition. You can apply it. Affine composition and norms, right? These might require a little bit more work. Easy to see these for gradients. Okay. In fact, many properties for gradients hold for subgradients. So if gx is f of ax plus b, then the gradient of gx is you can take the a outside, a transpose gradient of right. Sorry, ax plus b, the sub differential of f with respect to ax plus b. So a transpose has to come out. I mean, I can give an example here. Example will be easy to illustrate or understand. So let's say I'm looking at the sub differential of aw plus b, but let's say one norm, which is not differentiable. So in two norm also, if you had this, you would have put an A transpose that will hold for one norm as well. But only thing is now I'll be looking at the sub differential of the one norm of W. Okay. I mean, you get all of these examples we can see. So I can now make it more complex and I say, well, if I had to look at the subgradient for the addition part, right? I can say if I had to look at the sub differential of the one norm square, two norm W square plus say one norm of W. This by addition will just have 2 times W plus I will have the subdifferential of the one norm of W. Okay, so they are very handy. I mean, if you want to do anything in ML, you will be actually implicitly or explicitly applying these conditions. Another important special case is fx's the p norm of x, the last one. Right, so if p is um, 2, what happens? I mean, you can derive it, right? That we are familiar with. But p is 1 norm, it's we already dealt with the case. If p is 1, we dealt with the case of the convex hull. But for p between say 1 and infinity, what happens? Anyone? For p in say 1 comma, oh, right. So let's say p is between what can I say about the gradient? Does gradient exist for all of these? Does the gradient so I've used open interval 1. So at 1 I know it doesn't exist everywhere, but the gradient should exist for p greater than 1. It does exist. Okay. However, another very interesting way of writing the p norm. I mean, we saw in the case of p equals 1, recall. Let me use a different pen. Yeah. So you can recall that for the case of p equals 1, what I did was I said the one norm of p, sorry, one norm of x is max over s in -1 plus 1 raised to n s transpose x. Now, in general, can I say something like this? Is there a statement I can make an analogous statement? Anyone? Can I say that the p norm of q is similar max, but I cannot put a constraint like this. I mean, I may have to generalize that constraint. Max over something. Okay, so it turns out that yes, you can. Instead of using s, I'll use a z, or s is also fine. I'll just say s, but this is going to have some connection with the q. I'll explain what is q. Max of q norm of s less than or equal to 1 of s transpose x, where q is such that one upon p plus 1 upon q equals 1. Okay, so this is a very interesting exposure to duality. It's actually a dual relation between p norm and q norm. Okay, so the q norm is called the dual norm of p norm. And let's take some example. Okay, so there's some very interesting connection going on here. Right. So now I would like you to comment what happens if p is 1. And what is Q?
Infinite.
Right. So we have found another way of writing max. The way of writing max is not unique. It is one way of writing max. Okay, so if P is if P is Q 1, then Q is infinity and vice versa, right? So they are duals of each other. Oh, sorry. Right. So if P equals 1, Q is infinity. If P equals 2, what happens? Q will be what?
2 only.
2. So the 2 norm is a dual of itself. I mean, these come up a lot in duality analysis, etc. Okay, and you can basically verify, right? I mean, if this inequality, this equality is a kind of generalization of Cauchy-Schwarz, right? Do you see that? Why is it a generalization of Cauchy-Schwarz? Anyone wants to comment? Yes. How do I claim it's a generalization of Cauchy-Schwarz? Yeah, it'll be nice if you guys comment.
The dot product of S and X is always less than or equal to the P norm of X times the Q norm of S, where P and Q are duals.
Right. In that sense, it's a generalization. So it turns out that Cauchy-Schwarz is when P equals 2, right? And Q equals 2. That's what we use all the time. So yeah, Cauchy-Schwarz basically. So recall Cauchy-Schwarz. So what is that? Is basically absolute value of X transpose Z greater than equal to, oh sorry, so less than equal to 2 norm of X times the 2 norm of Z, right? Equality only if X equals Z. Okay, so that's the Cauchy-Schwarz inequality, and now we are saying, well, um, the equality holds as like max. So it's like saying that if I can write it differently as the max value is attained for the 2 norm, right? Max over all the Z with norm less than equal to 1, because this is less than, if norm Z is less than equal to 1, then this whole thing is less than equal to norm 2 norm of X. So this is the same as saying max over norms 2 norm Z is less than equal to 1 of X transpose Z. If you want, you can put an absolute value, it doesn't matter, but yeah, the same thing, because we know that X transpose Z itself is just less than equal to X, the absolute value of X. Okay, so this we're just generalizing from 2 norm to Q norm. So now we have X P norm is max over Z Q less than equal to 1 of X transpose Z. Okay, so that's exactly what we wrote here. Okay. Okay, so this is what we are trying to say. So this leads to a very interesting expansion for the sub differential of f. What would that be? Okay, so this requires a little bit more work. So all this is fine. This we have motivated. For such a Q, then somehow we can write down the sub differential of P norm of X, and it involves a Q norm. Okay, and it basically it's let me give you a hint, right? Like in the case of the one norm, I'm going to write in plain text here. Like in the case of the one norm. So in one norm, what we had was we had a kind of convex hull, a set of examples based on those points which gave you the maximum value, right? That's a support set, right? So this also can be expressed in terms of the support set. Okay, so I mean it's just the Q norm y such that the Q norm of y is less than equal to 1, and this y is the one that gives you the maximum index, right? So it's the same idea. And now this itself turns out to be a closed convex set. So if you want, you can put a closure and a convex hull, but this is exactly the set. It's a closed. You don't have to write the closure explicitly. It turns out to be convex set, which every sub differential should be. Okay. Can we derive the sub differential of the one norm of X? We have done that. It's already done. So we won't do it again, but it's going to be the same. But if you use the above, it'll be in terms of infinity norm. So the infinity norm, and that will turn out to be exactly this. Infinity norm. See, if you write this down, you'll find exactly what you had earlier coming up. So okay, so let's just for your understanding, let's try doing this. Let me just so different color. So if I start putting this constraint that the infinity norm of y is less than equal to 1, right? What would you get? I mean, infinity norm is looking at the max value, right? You'd get y, which is an element, if you want to maximize the one norm, which is an element of -1 plus 1 raised to n, because anyways you're looking at the max value, which should be less than equal to 1. If you want, especially if you say equal to 1, okay, now less than equal to 1, I would just push the frontiers and get it equal to 1. But if you say equal to 1, then this must be y. So this hint should be good enough. So you see this as a generalization. Okay. Turns out to be the same as what we derived earlier. Okay. So this is our first exposure to duality. And the whole idea of duality is interesting. This what I talked about in the previous slide, right? I mean, just to kind of close this generalization is called Holder's inequality. It's called. So the idea is Holder's inequality is that you have Z transpose X, which is absolute value less than equal to, okay, the Q norm of Z times the P norm of X, where for all P for all 1 upon P plus 1 upon Q equals 1. Okay, so just this generalization is pretty big. So I'll just this is an generalization. It's called the Holder's inequality. Okay, so this whole notion of duality is very interesting. If I want to make a sculpture, right? There are two ways I can make a sculpture. I can carve out a sculpture by molding, right? Make a mold, make a rigid frame. So that's one way of defining my P norm. My P norm, okay. So let me use the same slide. This actually is very interesting. So let's just look at this for a while. Holder's inequality. So there are two. Let's look at duality from this. So what is our exposure to duality here? So there are two perspectives of the P norm. Okay, so I can derive my P norm in two ways. One is, let's say, the two ways of making a sculpture. One is it's called the primal way, and in this case we'll illustrate a norm. So two ways of defining the norm. One is the primal way, which is what we are all familiar with. It's like casting, right? Casting. You fill up something, right? Fill up a mold. And that we are all familiar with. In terms of norm, we can write it as the P norm of X. We all know is basically summation I equals 1 to n of the absolute value of xi raised to p, the whole raised to 1 upon p. This we know. Okay. But now we are going to look at another way of the sculpture. What's the other way? That's the dual way. What's the other way you create a sculpture, a murti? Anyone? One is you fill up a mold, right? What's the other way you you create a sculpture?
Carve it out.
Yes, carve it out, chisel it out, right? The other is chiseling. I don't get the spelling properly. Yeah, chiseling maybe. Chiseling. Yeah, chiseling. Carving out unwanted stuff, right? Undesirable stuff, material from the amurti, right? From the material, the base object. Now, how do you get the same thing out here? So this is by discarding. Basically, in plain words, is discarding. How are you achieving the same thing in this Holder's inequality? Is there another way I can define my P norm? What is my P norm in terms of Q norm? I mean, in some sense, I did that here. This one, right? So instead of defining P norm directly, I defined it in terms of max over the Q, I mean, max over Z transpose Q of whether Z, the Q norm of Z is limited by 1. That's exactly the definition. Okay, so yeah, any questions? Okay. If there are none, we can probably move on. So now we are going to the lasso problem in machine learning, and we're going to now use all the properties we discussed so far and try and derive the subgradient. I'm going to make a small, slight simplification. I mean, typically we would have, here a ax, right? Y minus ax. So we've simplified y ax to just x. We are doing this because we know we can always use A transpose pre-multiplication, right? A transpose pre-multiplication. Can be invoked as per calculus of subgradients. Okay, so therefore, sometimes the simplifications you can do. If you don't understand what is A dash, I'll just put it as A transpose. Okay, so now what are the subgradients of fx? Yeah, just help me complete this quickly. Simple exercise. First part, what are the subgradients? What is the subgradient for the first part? It is differentiable, right? Gradient of y or 1/2 y minus x 2 norm square. It's a 2 norm square by default. This is nothing but, so this is with respect to x. Okay, so you may want to write it differently as x minus y norm square. Okay, so the same, but just bring x to the front, which is just x minus y. So that's done. And the second part we all know, as derived just some time back. What is this? This is s. Right, so now I have to compute the subgradient of x one norm, which is the same as max over all s, right? So we did all that. So this is the same as s, such that si is a sine of xi if xi is not equal to 0. Okay, xi is not equal to 0, it's a sine of xi. Okay, so I hope that's clear, right? Because this is because one norm of x is because of it's being max over s in minus 1 1 plus 1 of s transpose x. So it is going to be this s when you take derivative, but right, it's when xi is not equal to 0. But if xi is equal to 0, then what will it be? It will be si in, it's a convex combination of the signs, right? So it's a convex combination will just again be between minus 1 and convex combination of values between minus 1 and plus 1 will again lie within minus 1 and plus 1. Right? That is if xi is equal to 0. It's important to understand. Is this clear? We start looking like, okay, so the subgradients will start looking like x minus y plus lambda times s, where lambda times s will depend on what the value of x is at that point. Okay. I mean this just to clarify, this second part is exactly giving you the convex combination. I mean, in fact, the entire thing is convex hull, but the second part is largely because of the convex hull. That's why we. But as I said, all convex combinations of -1 and +1 values between them will always give you between -1 and +1. So we just written it as -1 to +1 range, closed interval. This is the convex hull of union over I of basically the indices SI at SI is max. Okay. Okay, so I mean, we always know that the issue is always at 0, right? So this, the reason we have special cased is because we know that the issue is at 0. Okay, so given this, right? So we've written this down: x minus y plus lambda s. Now, given this, we have an expression. Now we're going to use it for optimization soon. What I want you to do as homework is think of these next steps: composition with functions, where you have fx is p of qx, and we know that f is convex if qi is convex, p is convex and non-increasing in each argument, qi is concave, p is convex and non-increasing in each argument. We know this, and this is what gave us the log sum exp, right? This is how we showed log sum exp. Or one way we showed to be convex. But imagine now we want to derive the sub differential of log sum x. Sometimes it could involve also non-differentiable functions which are arguments to x. How do I now derive the sub differential? I mean, here are some examples, right? exp qx is convex if q is convex, and so on. We have seen these examples. I'm going to leave it as homework. Think of how you derive the sub differential, and my hint is go to the basic definition of sub differential. Work. Try deriving. I mean, you can Google and you can find, but try deriving, get the intuition. And a hint, use basic definition of the sub differential. Okay, which is basically in terms of fx greater than equal to fy plus h transpose x minus y, h transpose into x minus y. Okay, so I'm going to leave you with this homework, and we'll meet again on Thursday. So please also pay attention to the assignment that was updated, right? And we have a new deadline for that is February 27th. Okay, any questions? If none, then we'll close for today. Yeah, Ishan. Yes, Ishan.
So we always talk about sub differential at a point, right? So not
Right.
talk of function. So in the previous slide when you wrote, can you go to the one where we were doing the lasso?
Yes.
No, with your annotation. So here when you wrote okay, so you were bottom one, you were only having it at origin. The thing
This
you
one?
wrote in the thing you wrote in
Actually both are in terms of if xi is not equal to 0, it's sign of xi, right?
Yeah, so no, the one you wrote in the black, that is only at origin.
Ha. Yeah, correct. Yes, correct. But in general, you can write it as if si is max at x, right? So this
Uh,
is more complete. Is that okay?
yes.
Thanks then. Any other questions, or we'll close for today? Thanks. I think this level of interaction is helpful now. You've been more interactive. So please continue this. Keep it up.
Thank you, sir.
Thanks.